Thanks, Daniel. You know, there's a bit of a pattern emerging at these conferences, which is lots of very bright people that I respect immensely stand up and say very intelligent things. And then I stand up and take the complete opposite perspective. Today is no exception. So we've heard the word cloud lots. In fact, so much I should have bought a bell that I could sit at the front and ding it. And I think I'm going to take a view that isn't anti-cloud. I'm going to take the view that, yeah, cloud is great. Let's own it. Let's not have just good enough. Let's have the best of the technology, but the control that our customers frankly pay us for, rather than offloading that to somebody else. But I'm going to start with a story, and then I'm going to talk about the philosophy of this thing that we call the AutoPilot pattern, and then run through some examples of how we use it at Simwood in our containerization project. Before we go there, who has containerization live in deployment? Okay, so what, 7, 8 of you. Okay, who's heard of the AutoPilot pattern? Okay, 1. Have you really heard it, Alex, or are you just trying to be clever? Ah, good man. So, and who knows how to install Kubernetes? Okay, all right. So, in 1903, Orville and Wilbur Wright took flight. It was the first manned, powered flight in history. At the same time, there was a very well-known, very well-funded, because he was funded by the War Department, chap called Samuel Pierpont Langley, who was also trying to achieve the same thing. The Wright brothers had been trying since 1899, and nobody really had heard of them. But Samuel Pierpont Langley was trying to fly through brute force. He thought it was all about having an engine that was powerful enough to hold this plane up in the air. The genius of the Wright brothers was that they realized that actually somebody had to sit on this thing, and it needed changing characteristics. They had to fly it, and that's what they did. But man was obsessed with this idea of automated unmanned flight. And by 1917, we'd got to the stage of this beastie, which might look like a plane, but it's called a Kettering bug, and it was pretty much the first cruise missile. It was unpiloted. The engineer calibrated the engine based on how far it needed to fly, wind conditions, pointed it in the right direction, and set it off 75 miles, carrying its explosive to its target. Needless to say, it didn't return. In fact, getting to the stage of UAVs that could return didn't come until the 1950s or so, because there was so much parallel development going on that was essential to get to what we think of as a UAV today. And that actually happened in 1994 with the first flight of the Predator drone. And the Predator drone was used for recon in Yugoslavia. But even then, the guys that were piloting it had to sit in a van at the end of the runway where it took off. It was actually 2000 when it was armed and used in Afghanistan, where it could be piloted from the other side of the world. And it could fly 740 kilometers, spend 14 hours doing its meddlement and executing regime change and other such devilish things, and then return home. And that's what we think of as a UAV today. It took 91 years. Now, I wonder if Wilbur had said to Orville, what orchestration should we use? Or if they got bogged down with decisions relating to their flight that were just overcomplicating the situation. 2 things. I think the first thing, they'd have been paralyzed. At the very least, it would have taken longer to get to where we are today. Another possibility is that they made the wrong decisions. They felt compelled to decide on what choice of radio or what choice of other such thing, and they got locked into the wrong technology. And that would cost them time down the line because they'd have to go back and re-engineer things to remove that. Instead, they just flew the frickin' thing. And my point today is that we're in a very similar place with cloud and containerization. Containerization has assumed all of the nirvana that goes with DevOps. I don't disagree with any of it. As an end goal, it is absolutely fantastic. But if you're the company or you're the developer that is going from a few bare metal on-premise machines or a few VMs to a fully self-orchestrated, containerized platform with full DevOps philosophy involved, you're setting yourself a massive, massive task. And I think, well, are you doing that the Wright brothers way? Or are you doing it the Samuel Pierpont Langley way? When Simwood, we decided to go down the containerization route, aside from the choice of containerization technology, which you might think is the end of the line, there's a whole load of decisions to make. So the first one for us, and an absolute red line, and I spoke about this last year, was the network stack. Because the network stack in Docker, for example, is pretty horrible. The network stack in many cloud environments is pretty horrible. Principally because of that thing, that user land proxy and NAT and everything that sounds evil from a SIP perspective. So we took the view, if we're going down this route, we need to get rid of that. We want a container to be a first-class citizen on the network in exactly the same way as it used to be in a VM and a bare metal world. Whether or not it's in the cloud, on-prem, whatever. And we did that. The ultimate solution, the solution that's in production today, was BGP on the host, BGP in the container. So we start a container up, it knows its own network requirements. It announces those to the host and onward to the network. It knows its own security requirements. So through a protocol called FlowSpec, we spin it up, it announces those to the host, it announces those to the network. It's beautiful. And such you trace to any one of our services, and rather than you seeing router, host, the actual host you'll see in the path as a router. The container is the final path. And that methodology has given us tons of benefits. I talked last year at length about how we do Anycast and how much of a difference it's made to us and the services we provide. And I also made the point that people talk about Anycast in terms of big, global, sexy, aren't we clever type terms, but actually the biggest benefit from Anycast comes the deeper into the core of your network you go. So a simple example that this has enabled us is Redis. So we have dozens and dozens and dozens of Redis instances, and they're all Anycasted. You want to read from Redis? It's one IP address anywhere on the network. So that means if you have a container host running, say, Kamailio, that needs to query Redis, it will generally be querying the Redis that's on the local host. No network traffic involved, traffic's never leaving the host. Until that instance dies, or goes through the process of being restarted, in which case, Anycast enables you to talk to the next closest one. Again, beautiful, works great. The next question you face is, well, what about shared storage? Because coming from a virtualization world, you think you've got to have shared storage. How do we share state between these different applications? And you can do it in a containerized world, but it's pretty dirty. And as the guy that got through 7 SANs in 6 years, discovering bugs never previously known to man and natural disaster and anything else that you can imagine going wrong with a SAN, I quite like the idea of not having shared storage. We've got storage within the hosts. They'll survive a power cycle of a host. They won't survive destruction of a host. But thankfully, that problem's solved by the elapse of time, because most of the services we use are clustered now. So we may lose the data that's on a particular node if that node is destroyed, but there's other nodes in other sites, in other places around the network, other copies of that data. Unless we lose the entire network at the same time everywhere, then generally speaking, we don't need shared storage. Actually, in the scenario of losing everything everywhere, we'd lose the shared storage anyway. Service discovery, another one. Which service discovery products are you going to go for? Is it console? Is it etcd? It's all really confusing for your guy that just wants to install a freaking container and get started on his containerization endeavors. Now, there's a place for this. We chose console, but when we re-engineered the network, frankly, it didn't like us very much. So we ended up taking the simplest aspects of service discovery, clustered key value, store various other things, and putting them into an internal solution that we affectionately call Gaylord, which does much of what Consul does, but so much more. And then you come on to orchestration. How are we going to manage all of these hundreds of thousands of containers? Because we're going to be Google next week. Well, the reality is, most of us aren't. You know, we've got lots of hosts. We have many containers. But the reality is our scale, and our scale next week, is perfectly manageable manually or with Ansible and combinations in between. This isn't a problem. This isn't a problem that we need to solve today. Now, some of you may say, well, let's go with whatever the cloud says, because the cloud knows everything. Well, the problem with that is, A, it doesn't, but B, you're locking yourself into whatever decision somebody else has made. So you want to move to a different cloud provider, you know, maybe another one's cool next week. You're locked into, say you're with Google Cloud, you're locked into Kubernetes, you're with AWS, you're locked into some of their orchestration solutions. So I fundamentally disagree with that point. But you look at the very promise of containerization, and it was, and I quote, if it runs on your laptop, it will run in production. No, it won't, not unless you've got Kubernetes running on your laptop or whatever orchestration system you've chosen. So you're denying yourself one of the prime benefits. Now, don't get me wrong. I'm not saying that orchestration is unnecessary or bad. Kubernetes is fantastic. The others are brilliant too. I'm just saying for us, and probably most of you, it's a problem for another day. We don't need to solve it today. But we can get so much further on than we are today in a way that helps us when we deal with orchestration down the line. And that is with the AutoPilot pattern. I believe that a container should fly itself. Now, we're a good way there. We have a single image, we spin it up, it knows its network requirements, it makes itself work on the network. It knows its security requirements, it installs the necessary rules on the necessary points of the network. But you can go further than that. Take Redis, for example. Do you have a container image for a write node of Redis and another one for a read node of Redis? Or do you just have a Redis image? We opted for the latter, and it's an image that can discover its role and act accordingly using the AutoPilot pattern. And when things are in production, do you want to intervene? You haven't got this orchestration system to intervene for you. Well, how about the container flying itself and being intelligent, looking around it, understanding what's going on in the environment, and reacting accordingly? What we don't want to do is be SSHing into containers. Anybody that sticks SSH in a container should be shot. We don't want to be bootstrapping them and fanning about. We just want to deploy the image that we've got in a repo. And we don't want to need any orchestration platform. I'm not saying we never want to have one. We just don't want to be dependent on one. Because at that point, that container image will run on your laptop the same as it runs in production. And it will run on AWS the same as it runs in Google Cloud. Now, AutoPilot is not a methodology. I'm not going to give you a top 10 set of rules for how to do it. It's a philosophy. And really, I've articulated the philosophy on the previous slides. How you implement it and the extent to which you implement it is entirely up to you. And it's not my philosophy either. The guys at Joyent, who you may know for Node.js, and Triton, previously SDC, the cloud platform, they're pushing this. It's their intellectual property, if you like. And it's all out there on that URL there. If you want to read the blog Alex mentioned, that's our blog on what we do, particularly with Redis around it. But I promised you an example of how we did it. So we push a container out. And we may do that manually on the host, or we may use Ansible or some other means. Fact is, there's a new container or a new image, and it needs to go on a host, so we push it there. There's certain values that are going to change. For example, site name, because we have multiple sites, multiple different availability zones. We want the containers to react differently. That happens at the point that we push it. But let's take our Redis example. We push a new Redis container to a host. It starts up, and it's an empty database running Redis. It wants to know, what am I here for? So it can query a key value store, or it can query other points on the network and determine its role. So in the case of Redis, we push out a new node. It'll say, hey, where's the master? If it finds the master, it knows it needs to be a slave. If it doesn't find the master and there's certain other conditions, it knows it needs to become the master. But that one image is performing those multiple roles. In the case of Redis, we run quite large Redis databases, and we run a ton of transactions against them. So the last thing we want is a few dozen new slaves all connecting to the master and trying to pull the whole data set across. So our container image with AutoPilot, if a container's decided it needs to be a slave, goes to S3 or some other shared off-site storage and pulls down the latest backup and installs it. The master, conversely, is pushing those backups up periodically. At that point, the slave can connect to the master and do a partial replication of what's remaining. So we've now got our container. It knows it needs to be a Redis slave. It's got data, and it's replicating live from the master. At that point, it's ready for service. So at that point, it can say to the network, hey, I'm here. This is my Anycast IP address. And it can also tell Gaylord it's ready for service. Contrast that with other ways of doing this, where you start a container, boom, it's in service. This can be dependent on health checks and other conditions around the network, so that when that goes into service, it's absolutely ready for service. Beyond that, you want to change according to events. So there's different ways of doing this. One of the ways we do it is a given service, take Kamailio in a specific site, for example, consumes certain dependencies. Let's say FreeSwitch nodes behind it. So we'll have an endpoint such as that, which will list the status of all the FreeSwitch nodes in that particular site. And it will return something like that. Now that gives our Kamailio instance everything it needs to write an initial dispatcher.conf file, but it also gives it something that it can hash and poll, and if it changes because a new FreeSwitch node has come or gone, can trigger an event. Now bear in mind, we're not locked into pods or whatever the word is. This is just HTTP, or HTTPS only. So it can operate globally with cross-availability zone dependencies. You're not locked into a single site. But in the event of a change, it executes a script within the container. And that script could be bash, could be an executable, can be whatever you want. So within our Kamailio containers, the on-change event is, have any free switches come and gone? And the script is a bash script that rewrites dispatcher.conf based on where the Kamailio instance is, what FreeSwitch nodes are available, what the backup availability zone is, and it'll do that itself when any FreeSwitch comes and goes. But that's one example. I've given you the Redis example as well, and of course, you know, the hipsters would not forgive me if I didn't mention web services and load balancing with Nginx. Works in exactly the same way. So you want to do this. The easiest way to get started, and the way advocated on that URL I gave earlier, is console as a key value store with expiring keys, and a product of, well, not a product, but an output of Joyent called Containerpilot. Containerpilot just being a script that will wrap the executable within your container, and it will expose all of this good stuff like on-change to you. Now, once you get your head around the philosophy, you may well want to roll your own. You may well outgrow this. But that's a very easy way of getting you started with something sensible and tested, rather than me trying to abridge our solution in a way that makes sense for you. So where are we going with this? We want to put more inside the container, because whilst containers fly themselves to a large extent, There's a philosophical argument that takes place. You have two developers, you'll get three opinions. You know, in our case, one wants everything inside the container, one wants everything outside of the container, so the containers are super lightweight. They're probably both right, and the balance is somewhere in between, but I think at the moment we probably have more out than in. I want more in, such that every container essentially has an external API that exposes not only its state, but also telemetry that can be consumed by other containers. And we need to make a decision on orchestration, because whilst I disagree with much of what's been said about the cloud, many of the technologies and the products out there aren't bad. They're necessary at that point in scale that we're not, frankly, at yet. And with that, I don't know how I'm doing time-wise, so let's say thank you very much. And are there any questions? No?
Yeah,
Where's Nia?
thank you.
He must have something to disagree with.
Thank you, Simon. Are there any questions here? Questions?
Ole.
Sorry.
Oh.
Hi, I have a question about the diagram you had earlier in your slides about router, host, and container. I was wondering whether or not your container could directly
That
talk
one,
to you.
or that one?
The one with the green letters, correct. I was wondering, there are like, whether or not your container could talk directly to your router in this kind of example.
Yes. Yes, so the container is talking, well, sorry, yes and no. So the container is talking to the host, BGP. The host then assembles a collection of routes, which it announces to the router. Yeah, so no, it's not talking directly, but the routes are propagating there. Same with the flow spec rules, they're carried over BGP. Ole had his hand up, so.
Run, Henning, run.
So, as I said earlier, I'm a bit slow in uptake. I'll probably have a question in a year about this, but I have questions on last year's presentation when you discussed the software-defined networking and the new boxes and architectures and stuff. It kind of, if you go back a slide, you just say BGP, but does that stuff come in here, or are you still working on that? Can you explore that part?
So if I go back the year before last, I talked about white boxes and merchant silicon and SDN. That's that bit. So we're a fully switched network now in the sense that we're running layer 3 switches as opposed to big fridges, as I call them, routers.
With your own software?
No, we use Arista at that level. This is ours, or more often than not, in an implementation of GoBGP. There's a few ways you can go there. So you can use Quagga, which is big and heavy and a bit of a juggernaut, or you can use GoBGP, which is super lightweight and can either operate as a daemon or can operate as a library, depending which way you want to do it. So it's perfectly suited to go in there. So we've put GoBGP in there, GoBGP there, and then even if you use Quagga, you needed to use a thing called Zebra to actually manage the routes, and we found quite a few issues with that, removing routes. So we've written in Go a replacement for Zebra called GoBra, which actually manages adding and removing routes. So yeah, all ties together and all follows on. There's nothing changed in that respect. Any more for any more?
Anyone?
Okay.
Okay.
Thank you
Thank
very
you,
much.
Simon.
Thank you, Simon.